Hi, this is Jake from Impeller Operations. Today's topic is Turbomachinery design with OASIS CFTurbo ANSYS TurboGrid and CFX. We praise OASIS for state-of-the-art AI machine learning-based optimization algorithm and ease of use. OASIS has a one-click optimizer which is designed for high-dimensional and highly constrained engineering problems. There is no algorithm selection or parameter tuning. OASIS finds feasible and better performing designs with less simulation runs compared to other optimization software when benchmarked. Ease of use. No need to be an expert on optimization theory. One-day training is enough for OASIS to cover all aspects of problem definition, integrations, and intuitive post-processing capabilities. The usual optimization flow consists inputs and outputs, optimization problem definition, a simulation tool, or a combination of CAD, preprocessor, solver, and post-processor. User selects input variables, CAD dimensions, material properties, load properties, or other boundary conditions, and simulation outputs to be defined as objectives to be minimized or maximized, depending on the project goal. Input variables lower and upper bounds have to be set to define the search space. Cheap constraints are the mathematical relationships between design variables and have to be satisfied before the simulation call. Expensive constraints are dependent on simulation outputs. Users create optimization studies with expensive constraints to ensure certain design performance is met. This is the Impeller optimization problem definition, and there are 5 input variables, which are suction diameter, impeller diameter, outlet width, inlet and outlet blade angles. Number of blades, primary flow path, and other geometrical dimensions are fixed for this study. Any variable value in a CFTurbo batch file can be used in an OASIS optimization study. Cheap constraint enforces a geometrical criteria, and it states leading edge B star distance to be greater than the outlet width. The objective is to maximize the impeller efficiency. We also have an expensive constraint that states the head value should be in 35 to 45 feet range. CFTurbo ANSYS CFX and OASIS integration has 5 nodes. The driver of the optimization cycle is a PowerShell script, which is a pre-written template. ANSYS TurboGrid and CFX states have to be saved as session files. First node is the CFTurbo batch file, which is also the input file where OASIS writes the input values at the beginning of an iteration. Once the CFTurbo batch file is executed, it outputs a TurboGrid state file and an XML geometry file. The PowerShell script calculates the cheap constraint of the geometrical relationship. If it is satisfied, then node 2 TurboGrid session file is executed, which outputs the mesh file. The third node sets the domains, interfaces, and boundary conditions as per ANSYS CFX pre-session file and outputs the CFX solver input file. Fourth node executes the CFX solver, and lastly CFX post-session outputs impeller efficiency, head values next to the earlier calculated geometric constraint. This is the convergence plot for a 100 simulation call budget for the impeller optimization. There are 67 infeasible designs where head is less than 35 feet, and 14 designs did not meet the criteria of leading edge to outlet width ratio. 19 results satisfy all the constraints. First feasible design at iteration number 74, and OASIS finds the optimum, which is the maximum efficiency, at iteration number 85. This is the optimum design at iteration number 85 with 0.89 impeller efficiency and 44 feet head. Here is the velocity streamlines of baseline versus optimized impeller design. You can notice that the optimum design has a consistent maximum velocity at the outlet. I would like to finalize and recap on OASIS productivity and ease of use. So OASIS has no algorithm picking. It's a one-click optimizer, which is a state-of-the-art AI machine learning based optimization algorithm which finds feasible designs faster. One-day training is enough for OASIS. It's easy to build integration and automation for Turbomachinery design optimization, where you can have studies with single vane optimization, full impeller design optimization, volute optimization, or a combination of those different studies. In OASIS, there's also the concept of clustering of designs on the result sheet and also visually on the parallel coordinates plot, which makes post-processing easy and intuitive. This presentation summarized the OASIS capabilities with integration of CFTurbo, ANSYS TurboGrid, and CFX for turbomachinery design optimization. Thank you for your interest and attendance.